This is a video on the area of a polar region. The question states, use a double integral to find the area of the region that lies inside the cardioid, r equals 1 plus cosine of theta, and outside the circle, r equals 3 cosine of theta. So let's start by sketching a picture. So here's my picture. We have the cardioid here, 1 plus cosine of theta. And then we have the circle, r equals 3 cosine of theta. And we see that they intersect at 2 points. And we need to find those intersection points so we can find the limits of integration. So we do that by setting the r's equal to each other. And we get that 3 cosine theta is equal to 1 plus cosine theta. We can subtract the cosine theta from both sides and then divide by 2 to get that cosine of theta is equal to a half. And that occurs when theta is pi over 3, which is right here, and theta is 5 pi over 3, which is right here. It seems like we just integrate from pi over 3 to 5 pi over 3, but that doesn't quite work, because if we look at the polar region, you'll see that after pi over 2, the circle is kind of out of the picture. If we draw a ray from the origin to the cardioid, then the circle just isn't there. So we can actually split this into 4 different regions as follows. So we have the region in quadrant 1, the region in quadrant 2, the region in quadrant 3, and the region in quadrant 4. So normally we'd have to do 4 different integrals, but because of symmetry, the region in quadrant 1 and 4, those regions have the same area, and the regions in quadrants 2 and 3, those also have the same area. So what I can do is just double up each of these 2 areas to get the total area. So what I get is that the area is going to be equal to twice the area of the quadrant 1 region, and that will go from pi over 3 to pi over 2, that's the y-axis. And the lower curve, or the inside curve, is 3 cosine of theta, and the outside curve is 1 plus cosine theta, that's the cardioid. And then we add twice the area of the quadrant 2 region, and that is going to go from pi over 2 to pi. And the inside curve now is just 0, and the outside curve is the cardioid, which is 1 plus cosine of theta. And each of these have an r dr d theta, because when we have a polar area, dx dy is equal to r dr d theta. So I could work this out. I could integrate r to get r squared over 2, and then plug in, and then simplify, and then integrate some more. That'll be kind of a pain. Instead, I actually put this in my calculator, and what I got was that the total area is equal to 5 pi over 4 minus 3. And I'm done with the problem.